Welcome to this visual abstract and thank you for your interest in our research paper on failure analysis on boron steel components for automotive applications. The main focus of this paper is to show some drawbacks that can occur during heat treatments of automotive components made of boron steel. The automotive industry is continuously looking for an innovative mix of new steels and manufacture techniques in order to improve processing chain efficiency and cost reduction. To this aim, boron steels are becoming increasingly popular thanks to their high hardenability and machinability. Due to their reduced finishing steps, boron steels are commonly processed using fine blanking technologies. The success of fine blanking on boron steel components is due to heat treatments which must be carefully designed to avoid precipitation of boron-rich compounds that would lower steel hardenability. At high temperature, boron is very reactive with oxygen and nitrogen. An experimental campaign was performed on two different boron steels, namely En34 manganese boron 5 and En22 manganese boron 5. The steel samples were previously spheroidized and annealed in a neutral environment, hydrogen-nitrogen atmosphere, then fine blanked to obtain specific automotive components which were subsequently quenched and tempered. Three types of tests were performed: microstructure analysis with both optical and scanning electron microscope, hardness evaluation, and chemical analysis. Tests were performed at increasing distances from the surface to evaluate microstructure, hardness, and amount of carbon and boron all along the thickness of the sample, subjected to different types of heat treatments. Experimental tests reveal precipitation of nanometric compounds which act as nucleation sites for new grains when subjected to heat treatments above critical points. This effect blocks grain growth, triggers strong refinement of the grains, and drastically decreases the hardenability of the components. Moreover, the nanometric boron compounds diminish free boron, further reducing hardenability under the surface. The compounds are mainly localized below the surface and are almost absent at the core of the sample. Hardenability problems were brought back to nitrogen pickup during initial spheroidizing annealing treatments. The chemical analysis highlights that the progressive increase of nanometric compounds matches nitrogen increase beneath the surface, indicating a contamination of undissociated ammonia in the H2N2 productive atmosphere used on spheroidizing annealing. Thank you very much for your kind attention.